It's an alien landscape where magnetic tornadoes twist upward tens of thousands of miles. Mysterious dark spots, large enough to engulf the Earth, ebb and flow. And violent eruptions shoot tons of charged particles into space at speeds of over 2 million miles per hour. This is not some strange world on the other side of the galaxy. This is our sun. And now, new technologies are allowing us to see it like never before. Satellites are giving investigators new insights into centuries-old mysteries.
Whoa, did you see that?
Boom, there goes a flare.
That is really a quantum leap in solar physics, a continuous eye on the sun.
How does our sun work? Where does its power come from? And how can its inner workings impact us some 93 million miles away? Finding answers has a new urgency.
Before the expert by about 68 hours.
And the bigger hit.
The bigger hit.
Our sun has a dark side. Its violent storms capable of taking down the electrical grids that power our daily lives.
Repair could take weeks, months, and even in a worst-case scenario, up to 10 years for a full recovery.
If you can imagine a world without electricity, you're really going back in time.
Now, join scientists on a quest to understand the secrets of the sun. Dive deep into its core and ride out its spectacular storms. Right now, on this Nova National Geographic special. Dawn, February 15th, 2011, Boulder, Colorado. The team at the National Space Weather Prediction Center begins its day as it usually does, carefully watching the surface of the sun.
Okay, a 10 centimeter came in today.
Although 93 million miles away, forces here can impact Earth in surprising and destructive ways.
For the smaller,
The M6.
for the M6, you see this, the very first one is the M6.
Today, after years of relative calm, a satellite detects something. A dramatic explosion on the sun's surface. A violent solar storm that would dwarf Earth is erupting, releasing a massive shockwave, hurtling towards us at over 1 million miles an hour. Right now, no one is sure what to expect.
But I think that the M6 is going to get here.
We have to determine when that thing is going to impact Earth's magnetic field.
8 hours.
It's going to be sometime tomorrow, perhaps later in the morning, later at night. That's exactly what we're trying to determine. In fact, I have to join the discussions right now, so I'll get back with you.
The team models the approaching storm.
So 15Z for the arrival of the CME. This is it here.
Right
okay.
there.
Their simulation shows it racing out from the sun on the left towards the small dot on the right, Earth. The solar storm carries a 1-2 punch. First is a solar flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
The reports tell of auroras, brilliant displays in the sky. They're so bright that miners in Colorado wake up and go to work thinking it is dawn. Other reports tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of 2 massive CME waves.
Those 2 storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it.
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried, given more, concern right now. We'll be watching it, monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marveled when it's eclipsed during the day. And when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? These are some of the mysteries scientists must understand to protect us from the sun's darker side.
The sun can really surprise us.
The sun is elusive,
Crazy,
Complicated.
crazy,
Incredibly dynamic.
crazy.
With explosive potential.
The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years, and they conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
Geologists are familiar with this. By studying sound waves passing through the Earth's crust, they can see the layers below our feet. A technique called seismology. Similarly, sound waves moving through the sun's interior reveal how it's made up.
I can use this organ to illustrate how sound waves work inside the sun. For example, if I hit this low note, it comes from one of these big pipes, big deep sound. And on the sun, that corresponds to a wave that goes very deep into the sun and brings back the information from deep down in the sun. If I turn to a high note, it comes from a much shorter pipe, and on the sun, that's telling us information about very close to the surface of the sun, not very deep at all into the sun.
There are 10 million different frequencies resonating in the sun. Deciphering them leads to a seismic shift in understanding its structure, creating a new science, helioseismology.
Once the helioseismology came along, we could not only see what the surface was, but we could actually tell what the physical processes were underneath. So by looking inside, we can actually see what the sun is doing.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights, perhaps fancy TVs that I can't afford, but these are all plasma. Plasma is sort of all around you.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you're to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating plasma.
And it's under these extreme conditions that something really, really cool happens. Nuclear fusion.
It's the same atomic process inside the hydrogen bomb. Under tremendous pressure, protons in the plasma fuse together, releasing photons, minuscule packets of heat and light. An unimaginable number of photons are made every second, generating the sun's incredible power, some of which reaches us as sunlight. This atomic alchemy converts over 4 million tons of mass into energy every second in an endless loop.
That much mass into energy is the equivalent of 10 billion hydrogen bombs being created every second. The sun does this day in, day out. It's been doing it for 4 billion years, and it's going to continue to do so long after I'm gone.
The energy of billions of bombs is released in the core every second. This begs a simple question.
So you could ask, well, why doesn't the sun blow itself apart? It's because there's this beautiful balancing act that occurs. In the core of the sun, you've got this pressure from all of this fusion pushing outwards. And the sun is huge, so you have all this gravitational pressure pushing downwards. And so you've got gravity pushing down, and the sun trying to blow itself apart from the inside, and it is this beautiful balancing act between the two that keeps the sun in one piece.
This light, born at the core, reaches us after a remarkable journey. Away from the core, pressure and temperatures drop, and nuclear fusion stops. Now, each photon begins a tedious journey through the sun's thickest layer of plasma, a region called the radiative zone. Although squeezed less than at the sun's center, the plasma is still very dense, and photons struggle to move through it. Each packet of energy is continuously absorbed, then spit out by the plasma particles.
In that particular part, there's no energy being generated, but the energy is transmitted by the radiation. So that's why we call it the radiative zone, not too surprisingly.
The photons slowly bounce through the plasma here, ricocheting in a zigzag path called the random walk.
So imagine that you're in a crowded room and you're trying to make your way through, and you greet other people. And each person you greet, you have to say hello to, and then you move off in another direction. So it takes you a long time to get from one place in the room to another because you're just kind of meandering your way around the room. So the same way the photons in the inside of the sun, they don't have a preferred direction. All they want to do is they want to be moving, and they want to be greeting other particles.
Though moving at the speed of light, 186,000 miles a second, it takes photons over 100,000 years to cross the zone. Eventually, the photons reach a boundary where pressures drop again. The plasma thins, and moving through it gets easier. The photons still pack a lot of energy. Now, they leak out into the convection zone, heating it from below. The thinner plasma in this zone makes the photons move in a different way.
So instead of bouncing, all of a sudden there's an ordered motion. So it's as if all of a sudden someone said, lunch, and all the particles decided, oh, we all have to go this direction. And you still have to wait in line to get out, so it takes a month to get from the bottom of the convection zone to the surface, but it's a relatively short period.
During this short period, heat from the photons sends plasma here into perpetual motion, a maelstrom of churning 125,000 miles thick. Think of it like a massive lava lamp.
There's heat that enters at the bottom from the light bulb. It heats the material, and the blob rises to the surface. When it gets to the top, it cools off. And when it cools, it gets more dense and falls back down. This is a good analogy for what's happening inside the sun. We have the core of the sun heating the material at the bottom of the convection zone. The material expands, and it carries the energy upward until it gets to the surface.
These incredible images reveal convection at the sun's surface, rising and sinking plasma that creates a mesmerizing structure called granulation.
The granulation cells are about the size of the state of Texas. They only last for about 12 minutes, so there's an incredible amount of energy. It's a very dynamic, very chaotic place. And all of the activity is going on the surface of the sun where we can see it.
Photons produced at the core finally reach the surface. They emerge as a weakened form of solar energy. This weakened energy reaches Earth in 8 minutes. We know it as sunlight.
So 100,000 years, about a month, and then 8 minutes. Once you get to the surface of the sun, it just takes 8 minutes to get to where you can see it.
Unimpeded, the trip from the core to the surface would take the photons a matter of seconds. In reality, the sunlight that shines on us today may have been created during the last ice age. Energy reaching the sun's surface doesn't just result in sunlight. It can also trigger solar storms. Understanding the sun's destructive power requires 24-hour precision surveillance, something that, until recently, was impossible to achieve.
5, 4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory.
February 2010. NASA launches its most sophisticated solar satellite yet. The Solar Dynamics Observatory, or SDO for short.
Coming up on Mach 1.
SDO is the first satellite to deliver almost continuous, super high resolution coverage of our nearest star, giving researchers unprecedented access to the sun and its secrets.
The first day was very exciting. We knew we were going to open our doors to actually let the sunlight into the instrument for the first time.
We started looking at the first pictures, and it was almost in focus. And as soon as we focused it, it was just beautiful.
The new images reveal the sun like never before. An alien landscape where strange structures ebb and flow. Giant tornadoes, hundreds of thousands of miles high, that could easily engulf the Earth. And superheated bubbles of plasma the size of Alaska.
When I look at the pictures, I think they're really beautiful. I'm struck by the dynamics of it. Things are changing all the time, no matter where you look. And I'm also pretty daunted by the complexity of it all.
That's not surprising. Previous satellites only revealed a portion of the sun in high resolution. Now, they see it in mind-boggling detail.
Now, in order to look at the Solar Dynamics Observatory images that we're bringing in every day, we've built this very special wall, which is 9 high-definition television screens together that can display these images, so that the instrument and the display system together are an entirely new way of looking at the sun.
We can see all the details of what is going on, and that is really a quantum leap in solar physics. Being able to see all of that all the time, a continuous eye on the sun.
One of the most important aspects of SDO is its ability to see sunlight across a range of wavelengths, the equivalent of looking at things glowing at different temperatures. Our eyes are most sensitive to sunlight glowing at around 10,000 degrees Fahrenheit. At this temperature, the sun's surface looks almost featureless. But at hotter wavelengths, normally invisible, a far more dynamic picture emerges. The February 15, 2011 storm is a perfect example. In this repeating image, at around 90,000 degrees Fahrenheit, SDO captures just a ghostly trace of the CME wave. But at just over 1,000,000 degrees, the superhot plasma rippling away from the eye of the storm is much clearer. This allows researchers to see coronal mass ejection waves evolving across the entire sun.
This is an absolutely amazing time for solar physics because of these beautiful high-resolution images that allow us to understand better the physics behind what's going on when solar storms erupt.
Was that one last photo? Look at this one.
Back at the National Space Weather Prediction Center,
That's the M1 here.
Bill Murtaugh tracks the storm's CME wave. It carries 1 billion tons of plasma.
Well, we're right now
and is now only about 20 hours from Earth.
We're bringing it in mid to late on the 17th into the 18th.
What they see is alarming.
Well, there's actually 3 CMEs that we're looking at. So we bumped up some numbers for late tomorrow. Yeah.
It's not a single CME wave, but 1, 2, 3 of them.
We won't call it the perfect storm yet or anything, but conditions are lining up for some significant space weather.
Their models show trajectory and speed, but the big unknown for Murtaugh is how powerful the waves will be when they hit. The answer lies in a force that governs the sun: magnetism. We're all familiar with magnets. They produce an invisible force that pushes and pulls on charged particles. In fact, Earth has a magnetic field that protects us against threats from the sun. But we are less familiar with the sun's magnetic power, which researchers believe plays a major role in driving solar storms.
We've essentially learned that it takes 2 things to make a star magnetic. It needs to have these convective motions right underneath the surface, the bubbling of the gas. It needs to spin, and the faster it spins, the more active it becomes. And wherever those 2 things, the bubbling and the spinning, can interact, that's where we see the strongest magnetic activity in stars.
Astronomers know that the surface of the sun spins in a strange way. Travel from the poles of the sun towards its equator, and you'd notice it turns faster. Analyzing sound waves inside the sun reveals that the plasma layers beneath the surface also spin at different speeds. That's because they act like fluid, which gets denser towards the core. The interior of the sun is a place of spectacular turmoil. Turmoil that's the key to the sun's magnetism.
The motions there, the convection, the differential rotation, the motion from equator to pole, are driving a new force. They're driving a magnetic field. There's a dynamo at work here. A dynamo that's generating a force that we actually experience here on the Earth.
It works like a giant wind turbine. Churning plasma in the convection zone stirs up powerful electrical currents, which generate a huge magnetic field.
Have upflows here and downflows coming down this way, right?
The holy grail for scientists is understanding exactly how this dynamo generates solar storms. The clue lies deep within the convection zone. Magnetic field lines normally run from pole to pole. But with all the turmoil in the convection zone, that pattern can't last. Rotating layers stretch them horizontally. Convection twists and braids them. Under immense strain, they begin to kink upwards towards the surface.
Imagine this spring is a magnetic field line. The magnetic field inside the sun is amplified, is strengthened by the rotating motions and the shearing motions and the churning motions inside the sun. It wants to expand upwards, and it does, until it pokes out through the surface of the sun.
Tracking invisible field lines is normally impossible. But plasma plays a critical role.
Even though the magnetic field lines themselves are invisible, the plasma, which is heated and hot, can light up along these paths. In maybe the same way, you could think of a highway, and at night you wouldn't see the highway at all, but with the cars with their headlights on, you'd see the path of the highway.
Watching field lines is critical to understanding solar storms. As field lines emerge, they form loops. One end has a positive pole and the other a negative pole. Churning plasma beneath the surface twists these loops, pumping them with energy. If twisted enough, positive and negative parts of the loops cross. When they do, they short circuit with a tremendous explosion. The energy released heats the plasma to millions of degrees, resulting in a spectacular solar flare. It's the final dramatic stage of a very long journey. Photons formed in the core make their way to the surface. Some pass directly into space as sunlight. But in the process, that surging energy disturbs the convection zone, generating a magnetic field. The field lines wind up to the point that it explodes in a solar flare. Now, SDO provides a complete and unprecedented picture as these events evolve.
This is beautiful because the hot gas outlines the magnetic field lines that we would otherwise not be able to see. And here you can see even a twisting structure as some of the mass drains back down to the surface, and a lot of it escapes in the eruption. This is the essence of space weather, or solar storms.
This explains how flares form, but it's not the end of the story. Crossing magnetic field lines can cause nets of plasma to be flung into space. This is a coronal mass ejection, a CME wave. The portrait of how solar flares and CME waves form is coming into focus. But a key question remains. CME waves can travel 93 million miles to Earth in a matter of hours. So what gives them such explosive energy? Part of the answer is hidden here in the sun's atmosphere, the corona. It's made of superhot plasma that blisters at over 3 million degrees Fahrenheit. 300 times hotter than the sun's surface. Some scientists suspect that this heat powers massive gusts of energy that blast CME waves toward Earth at incredible speeds. But why the corona is so hot is an enduring mystery.
Understanding it's essential if we want to get to the bottom of how the sun drives space weather and the impact of the sun on the Earth.
The fact that the corona is so much hotter than the surface flies in the face of physics.
The sun's corona is a very odd place. Take this fire, for example. As I put my hands close, sure, it's warm, but as I pull them away, it gets cold. That's not the case on the sun at all. As you go in close, it's definitely warm, but as I pull away, it actually is warmer still.
Recently, Japanese investigators observe high-velocity jets of plasma shooting up from the near surface. McIntosh suspects these jets deliver heat to the corona, but he doesn't have a way to confirm it visually until he turns to SDO for help.
Lo and behold, we actually managed to join the dots and see, yeah, these objects that we could see moving out of the lower atmosphere at high speeds, kind of like these licks of flame really were reaching a couple of million degrees. It was really a tumultuous moment. We kind of looked at each other and said, wow, what have we just done?
They've shown that the plasma jets accelerating upwards from near the sun's surface generate tremendous heat. As a result, temperatures in the corona soar to 3.5 million degrees. If confirmed, it represents a huge leap forward in understanding CME behavior. The immense heat of the corona acts like a wind in a raging gale. It's constantly pushing on the plasma draped on the field lines, billowing them out like sails pulling on a mast. Like solar flares, when magnetic lines cross, there can be an immense explosion. In this case, the lines are cut and the sail whips off into space. Loaded with 1 billion tons of highly charged plasma, the CME wave can wreak havoc on electricity-dependent Earth. At the National Center for Atmospheric Research, this violent event is captured by satellites.
Now, to see the CME, we need to create a little artificial eclipse. To do that, we block out the light from the disk of the sun, and that's this little circle here. But what that allows us to do is to see this extremely faint, high-speed thing shooting away from the sun. This one moves at about 1,000 kilometers per second.
By enhancing the picture and slowing it down, it's possible to see the shockwave moving at over 2 million miles per hour. Though we have a better understanding of what causes solar storms and how they reach us, there is still a final pressing problem.
Trying to predict when solar storms are going to occur on the sun really requires a lot of detective work. Basically, we're looking for clues and observations to tell us when potential storms might occur.
The best clue comes from these. Sunspots. Dark patches which can linger on the sun's surface for weeks at a time.
A sunspot is a massive region, several times the size of the Earth, which appears on the sun as a dark spot. It's dark because it's relatively cool compared to its surroundings. And it's cool because the magnetic fields are so strong that they're suppressing the flow of heat from below.
The strong magnetic fields which create sunspots are the breeding ground for solar storms. The challenge is trying to decipher a pattern for when and how many will appear.
As we watch sunspots over a period of many years, we see something very interesting. The number of sunspots at any given time will wax and wane over a period of about 11 years. And since we now know that sunspots are associated with strong magnetic fields, this tells us that the sun's magnetic fields are likewise going through a cycle.
The constant churning and twisting inside the sun creates a powerful dynamo, the biggest electrical generator in the solar system. The magnetic field lines it produces get so wound up that roughly every 11 years, the magnetic poles of the sun reverse. After that, calmer magnetic activity prevails and fewer sunspots form, a period called solar minimum. But because of the sun's turbulent nature, the field gradually winds up again. As it does, magnetic outbursts are far more common, a period called solar maximum.
The solar cycle actually determines the personality of the sun. During solar maximum, it can get very angry and it can throw off solar storms that are sometimes directed at the Earth. And during solar minimum, it becomes much more subdued. There aren't as many sunspots, there aren't as many solar storms occurring. The activity cycle basically determines how the sun is going to act.
Prior to the solar storm of February 15th, 2011, things were pretty quiet on the sun. But that outburst marks an ominous turning point. The sun's magnetic activity is winding up again, as it heads towards solar max. Just a few days ago, Bill Murtaugh and the team at the Space Weather Prediction Center witnessed the turn.
Arrival of the X2 and the M6, if it comes in with any geoeffectiveness, between 12 and 1800.
So that's what we're seeing.
It's now time to let the world know what it might expect.
Nothing higher than 2.
In the next couple of minutes here, we're going to have to make a decision and make the prediction that this coronal mass ejection is going to arrive at whatever time tomorrow, and the geomagnetic storm will ensue, of course, once it arrives.
With the event we had...
Murtaugh knows that the severity of the storm depends mainly on two things: how strong the CME's magnetic field is, and at what angle it hits Earth's own magnetic field. CME waves approach Earth like a slowly rotating shield. One end is positively charged, the other negative. With magnetism, opposites attract, and like poles repel. If the wave's positive pole lines up with the Earth's positive pole, most of the power of the storm will be repulsed. But if opposite poles line up, the plasma the waves are carrying will hit with full force.
Did you say it came in at 115?
114.
Murtaugh makes his final assessment only hours before impact.
It could be larger, more complicated, typically, than just your single coronal mass ejection.
I think we nailed the forecast.
Okay. I'd like to think so.
According to the observations, the CME wave will be repelled.
We don't expect it to be too strong. We'll see moderate storming levels, which is good enough to produce some aurora borealis down in the United States, down along the Canadian border, northern tier states, and it will cause some minor problems to the power grid and whatnot.
Space weather for the next 24 hours is expected to be minor. Radio blackouts reaching the R1 level are expected.
This time, we dodged a bullet. But disturbing evidence suggests the Earth will not always be so lucky. It's a cautionary tale. NASA's Jim Green discovered it while researching a book on the American Civil War at the Library of Congress. Green found news accounts from 1859, which caught his eye.
I would run across articles about aurora, fabulous aurora, and this really piqued my interest because it's in my field. It seemed as though the armies of heaven were engaged in terrific, though noiseless, conflict. This terrific aspect soon subsided into a more beautiful and brilliant appearance, a few of which I can only refer to.
On the day before the waves hit, a British astronomer observes a giant sunspot group light up with two massive flares. The second CME wave hit 18 hours later, allowing Green to calculate its speed, 5 million miles an hour, plowing into Earth at almost 4 times the speed of the February 15, 2011 CME waves. Using the various reports, Green is able to reconstruct the 1859 storm. The accounts suggest that the poles of the CME waves were aligned, and instead of being repulsed, the waves hit with full power. The charged particles funnel down into the atmosphere, electrifying it like a giant neon sign, producing dazzling aurora displays. The storm is so intense, Earth's magnetic field all but collapses. Millions of tons of plasma spill towards the equator, and a powerful electric surge pulses over the globe. For the largely pre-electrified world, the moment passes with minimal damage. That might not be the case today.
It has the potential of knocking out power grids. And if it burns out transformers that are hard to replace, we may be without electricity in many areas for a very long period of time. There's only a few places that make these 125 kilovolt transformers. It takes several months to make them. And if you burn out half of them, we're going to be shooting squirrels and chopping wood out the backyard for a long period of time just to survive.
Everything grows,
building up.
but the 3Ds really...
Today's solar scientists believe it's not if, but when the next big one will strike. With the next solar maximum due in 2013, it begs an all-important question. Can we predict when the next solar storm will hit?
No.
Maybe.
No.
Maybe.
No.
Maybe. And the reason why is we've learned so much about the sun. We're getting better at it, but we have a long way to go. And the more we look at some of these historic events, the more we get a deeper appreciation for what we need to know.
Today, we see the sun better than ever before. We're beginning to understand it from the inside out. But its unpredictable personality means there will always be uncertainty when living with a star.
Hi, I'm Yul Kwan from the new PBS series, America Revealed. Come, dive deeper, and reach beyond with Nature, Nova, and America Revealed. All in one night, all in one place, right here on PBS.
This Nova program is available on DVD and Blu-ray. To order, visit shoppbs.org or call 1-800-PLAY-PBS. Nova is also available for download on iTunes.